To illustrate more clearly the repercussions of having an irreversible and reversible process and the differences between the two, I want to introduce to you the concept of a heat engine. Okay? And so in engineering, our namesake, engines are processes or devices that just convert some sort of input into a work. Right, that's just the basic definition of an engine. So they convert an input to work. Right? And more specifically, a heat engine is an engine that takes heat and converts it to work. So Q to W. All right, and so we're going to explore the concept of heat engines, and we're going to compare two different types of heat engines. One that undergoes a reversible process, and another that undergoes an irreversible process. And so the heat engine we're going to talk about is we're once again going to revisit a piston cylinder sort of system. And so initially in state 1, we have a piston cylinder with a gas underneath. And the gas is initially compressed. Right? And then there's like a lock above the piston that holds it in place. Right? And so the system is initially at some pressure 1. Right? And we're going to give this system also some more numbers. And so the amount of moles in the system, there's 8.07 moles of gas in there. It's at an initial temperature of 25 degrees Celsius or 298 K, and the initial volume is going to be 0.1 meters cubed. Okay? And then what we're going to do is we're going to do two things. We're going to expand the system isothermally, and in order to achieve that, what we're going to do is we're going to add heat to the system, and then we're going to release the lock. Let me write that better. Release lock. And so by doing these two things, this allows the gas to undergo an isothermal expansion, so that the temperature stays the same, but the volume is going to change. Okay? And so we'll add some heat, and the amount of heat we're going to add in is 10,000 joules. Okay? So we add in the heat, and then we release the lock. And by doing that, that causes the system to undergo an isothermal expansion. Where the system is now at some pressure 2. The amount of moles in the system, still the same. It's an isothermal expansion, so the temperature didn't change. But the volume is now 0.165 meters cubed. The other thing I'll say is that all throughout this entire process, atmospheric pressure stayed at 1 times 10 to the 5th pascals. Okay? All right, and so this is the premise, and these are the initial and final conditions of our system. And what we're going to do is we're going to compare, we're going to use these initial and final conditions for both the reversible and the irreversible processes. Okay? So first, let's consider the reversible process. And so for the reversible process, if we begin with an energy balance, we have a closed system, and we're going to write the differential form of the energy balance. Okay? In this system, it's isothermal, so change in internal energy is equal to 0, and assuming this is an ideal gas. We'll also assume that changes in kinetic and potential energy are also negligible. Okay? So the only ththings we have left are dq and dw. Okay? And so for the reversible process, the Q reverse is going to be equal to the negative dW reverse. Okay? And we know for mechanical work, the negative dW reverse is just P gas times dV. And if we apply the ideal gas law, then we have this equation. Okay? Alright, and so then if we integrate, what we get is that the Q reverse is equal to nRT ln of V2 over V1. Alright? And if we plug in the volume, V2, V1, and the nRT values that we have, what we get back out is 10,000 joules. Right? And so that's the work, essentially the negative of the work that we put in is equal, or the negative of the work that we get out of the system is equal to the heat that we put into the system. Okay, so that's equal to Q in. And so just to summarize the point here, for a reversible process, all input heat is turned into work. Okay? So that was the case for the reversible process. Let's now consider the irreversible process. Okay? And so if we start with the energy balance, the left-hand side is still all equal to 0 because it's still an isothermal expansion and there's not going to be any major changes in kinetic or potential energy. Okay? And so if we rearrange it, we can write it in terms of irreversible work and irreversible dq. We have this. Okay? Alright, and so we have dq irreversible is equal to the negative dw irreversible. Alright? And in the irreversible case, we're going to kind of think back to all those examples we thought about earlier, where we saw that the work was going to be equal to just the force that the system is acting against times the displacement. Right? And so, just to maybe make this a little bit more clear, what we get down, or what we get is that it's going to be force down dx, which we could write as pressure 2 times the area of the piston dx, and we could combine everything so that it's pressure 2 times the area of the piston. Okay? Alright, and so to get the Q irreversible for this system, all we have to do is integrate. And so we get Q irreversible is equal to P2, because this is a constant now, times volume 2 minus volume 1. And if we take the volume 2 and the volume 1, same parameters that we used for the reversible process, if we plug those in and multiply them by pressure, what we get is 6,500 joules. Okay? And so this number does not match the amount of heat that we put into the system. Okay? And so there's a discrepancy here, right? Essentially, our energy balance is not closing, right? Because the amount of work that we extract from the system is, its magnitude is not equal to the amount of heat we put back into the system, or we put into the system to begin with. Okay? And so what's going on here? And so what's going on here? Our energy balance isn't closing, right? The heat, the total heat associated with the irreversible process is not equal to, the magnitude's not equal to the work we get out from the gas as it expands. Okay? And so because this energy balance isn't closing, right, if we only consider the Q that we put in and the work that we get out, what that tells us is that there needs to be another term in our energy balance in order for things to be consistent. All right? So if we go to the next page here, essentially what I'm trying to say is that for the irreversible energy balance, in order for it to actually work, some energy put into the system, that was put into the system as Q in, put into the system as Q in, or from Q in, maybe. That must be released from the system as another form of energy transfer, like heat. So we could call that Q out. Okay? And so essentially, to illustrate with this idea, if we take a look at our piston cylinder, so we have the piston cylinder here, we have the gas that is expanding, and so essentially we put in heat into the system. Some of it, of the energy that we put in, is transferred directly as irreversible work, but another segment of that energy is going to leave the system as Q out. Okay? Right? So that's where the energy that's going into the system leaves under two separate mechanisms. Okay? And so if we revisit our energy balance, essentially what we have is, on the left-hand side, it's still 0. But on the right-hand side, what we're going to have is Q in plus W plus Q out. Okay? And we know, this should be WIRR. And if we move WIRR to the left-hand side, we know that's equal to P2 times V2 minus V1. And that's going to be equal to Q in plus Q out. Okay? And this, on the previous page, is what we called Q irreversible. Okay? And so that means that the Q out, the heat that leaves the system, is just going to be equal to Q in minus that Q total irreversible. So it's going to have a value of 3,500 joules, right? And so that negative sign is important because this tells us that this is heat that's leaving the system. All right? And so if you're going with an irreversible process, if you add in heat to the system in order to perform work, not all of that heat is going to turn into work. Some of it leaves the system as what we call lost heat. Okay? And so to summarize, irreversible engines do not convert 100% of input energy into work. Right? And this concept, or this Q out variable that I illustrated up at the top. The way to physically think about it is you could think of it as lost work. Or another term that people use is waste heat, right? And it's considered to be waste because it's energy, it's valuable energy that you put into the system that you paid in order to extract work out of your expansion, right? And so that's energy that's not being used to perform work. That's the idea. Okay? And so this Q out is going to go from the system to the surroundings. And essentially, if your goal was to make as efficient of an engine as possible, what you would want to do is you would want to minimize the value of that Q out, or the magnitude of Q out. So if you want to make an efficient engine, you need to minimize Q out. All right? And so in this example, I kind of gave a very like overspecified way of discussing, this sort of lost work or this waste heat that leaves the system. Okay. But more generally, if you want to estimate how much the magnitude of this Q out, what it would be, if you want to do it a priori, right? In order to do that, we're going to need some other equation that allows us to calculate that ahead of time.